This is a video for section 2.4 of Unit 2, and it is about the structure of metals and alloys. So we start off by looking at right here, metallic lattices. And remember, lattices are like the kind of configuration of all these compounds that have opposite charges, and they form these kind of structures that benefit from the strong interactions that the positive and the negative charges would have with each other. And here we go, we see Coulomb's law again. And Coulomb's law is just that the forces of attraction, the attractive forces, are based on the two charges divided by r squared. And the melting points can be used to compare the strengths of the metallic bonds. For example, mercury is at a liquid at room temperature, and cesium melts at 28.4 degrees Celsius, while tungsten melts at 3,680 degrees Celsius. So the higher the melting point, the stronger the lattice and the strength of the bonds. Okay, let's look at this next bit. Okay. Metals can form alloys so easily because replacing one metal atom with another metal atom rarely disrupts the strength of the metallic bond. Okay, so replacing one metal with another metal atom rarely disrupts the strength of the metallic bonding. Okay, for example, an alloy of sodium and potassium can be made, but the alloy formed is liquid at room temperature, showing that the metallic bonding is slightly weaker. So I believe this one is the potassium, and they've potassium, all potassium here, and this one is potassium and sodium. But I guess these bonds are not as strong, and so this is liquid, whereas this one is solid. Okay. Alloys can be divided into two main categories: substitutional alloys and interstitial alloys. So we should know what that is by the end of this. These alloys are both homogeneous mixtures. Homogeneous just means one thing in the mixture, in which components are dispersed randomly but uniformly. This type of alloy formed is largely determined by relative atomic sizes. So here we see the difference between the substitutional alloys and the interstitial alloys. So substitutional alloys are formed when two metallic components have similar atomic radii. So for it to be substitutional, there have to be similar atomic radii. And thus, they'll have similar chemical bonding characteristics. So if they have a similar atomic radii, they'll have similar chemical bonding characteristics. Brass is an example of substitutional alloys. Zinc and copper are a very similar size, so the original structure is maintained, though strengthened. Okay. This alloy retains properties such as malleability, ductility, as metallic bonding is easily reestablished. Interstitial alloys are formed when the atoms are much smaller than the main metal atom, and we see that here. I'll scroll the page down. Typically, the interstitial element is a non-metal that makes covalent bonds to neighboring metal atoms. So let's look at these interstitial. So steel is an interstitial alloy with much smaller carbon atoms in the spaces between the iron atoms. And we see that here. These very small carbons and these very large irons. And so that's an interstitial alloy. The presence of the carbon atoms enhances the structure. So steel is harder than the original iron. Oh wow! So steel. So there we go. This creates steel. But it'll be less malleable. Well, that makes sense. It's more reliable and it's more stronger. So it'll be easier to bend and fold. So steel, much harder than iron. Okay, the wide variety of alloys makes it difficult to make accurate predictions about properties. But in general, alloys will be poorer conductors, less malleable and less ductile, but much stronger. So they will be poorer conductors of electricity, less malleable and less ductile, but stronger and harder. Okay, also in general, smaller atoms that are able to form interstitial alloys will have a more disruptive effect on metallic bonding, making it harder to displace atoms, resulting in stronger alloys. Okay, boom. So, based on just the minimal information, I think these questions should be fairly easy. Copper and zinc atoms have the same exact atomic radius, 135 picometers. Based on the information, which the following represent an alloy containing... So it's, if they have the same radius, it's definitely not this one. And it's definitely not this one. And this would be all the same thing, so it's definitely not this one. Leaving only this one, B. Okay. A particle level diagram of a metallic element is shown opposite. So this is a metallic element. Typically, metals are both malleable and ductile. The best explanation for these properties is that the electrons involved in bonding among metal atoms are are they unequally shared? That doesn't look like the case, so I would cross out A and B. It does look like they are equally shared, all these negative charges up and down, right? And they form a non-directional bonds, or they form highly directional bonds. So I think they form highly directional bonds, right? Because these bonds that they're forming are here, 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 and here. Do they mention that in the earlier chapter? Earlier in the chapter? Short distances. And yeah, it seems directional because where else would the bond form? How else would the bond form? Okay, moving on. Question number 3. Steel is an alloy containing iron and carbon atoms. Which of the following diagrams best represents the particle structure of steel? So now, to my understanding, carbon is a lot smaller than steel on the periodic table. The radius should be much smaller. So this is not real, right? Because carbon is like atomic number of 6. And let me check my periodic table. Iron has a atomic number of 26. So iron is considerably larger than carbon, right? So it's definitely not this. They're not the same. Carbon's not bigger, right? I don't know what's going on here. Why would carbon sometimes be bigger and sometimes be smaller. I don't know what's going on here. Just by the process of elimination, I've been able to figure out this. Not to mention that they said this, and this is interstitial, right? Interstitial, we just talked about, and which is where the smaller one is kind of in the crevices. And we saw it with iron and the carbon. Oh yeah, this is steel. This is the one we just looked at. This is steel, and it's stronger than iron, but it's not as malleable, and it's not as. So, anyways, long story short, this is the answer. Okay, question number 5, or 4, I should say. Okay, it says element is gold, copper, silver, and these are their radius. This is their melting point. This is their common oxidation state. To make gold stronger and harder, it is often alloyed with other metals such as copper and silver. Okay, to make gold, and this makes sense when you buy gold chains. A lot of times your options like 14 carat, right, or 18 carat, or what's the other one? 10 carat, right? They're mixed in with copper and silver, because those are also a lot cheaper. But they make it also, it's stronger and harder, right? Because gold is not very strong. Anyways, consider 2 alloys, one for gold and copper, and one for gold and silver, with the same mole ratio of gold. If the gold and copper alloy is harder than the gold and silver alloy, which the following is the best explanation from the table above? Okay, let's see. Copper has 2 oxidation states and silver only has 1. Copper has a higher, let me adjust this. Is there no other way? Is it just the one side or the other? Yeah, I guess so. And what did they mention here about the melting point leads to strengthening of the bond, right? So we want a higher melting point. So let's see, they did mention melting point here. The melting point of gold is really high. And so copper, they're going to mention. And here we go. Copper has a higher melting point, but Ag has a lower melting point. And that's the answer. They talked about it in the chapter. So I didn't mean to make this look like it got crossed out. I was trying to underline it. But here we go. So it's B. Okay, that was pretty easy. Which of the following best depicts an alloy of nickel and boron? Now, if I look at my periodic table, nickel, gotta find it. Nickel is Ni, I believe. Yeah, nickel has much larger. It has 2 additional, possibly 3 additional rings. It has a 20 atomic number of 28, and boron, I believe, is just a good old 5. Right, so nickel is a lot larger. So this could only be one thing, and it's A. It's interstitial. Again. Okay. Now this is bigger than the page. Okay, let's see here. Steel is an alloy consisting of iron and a small amount of carbon. We learned that today. Elemental chromium can be added to steel to make the steel less likely to rust. Chromium atoms react with oxygen in the air to form a non-reactive layer of chromium oxide on the surface of the steel, preventing the oxidation of underlying iron atoms. A sample of steel chromium alloy contains 15% chromium by mass. Which of the following diagrams best show a particle-level view of a surface section and interior section of the alloy represented to the left? Okay, so I guess this is the surface and this is the interior of chromium ions to steel to make it less likely to rust. Chromium ions react with oxygen in the air to form a non-reactive. A non-reactive layer of chromium oxide on the surface, preventing oxidation. All right, because that's the thing with steel rusts. You ever see like a bike chain or something like that? It rusts. And so here they talk about the mass and atomic radius. Okay, so they talk about this thing being on the surface, right? So first of all, so I guess the question is asking which of these, right? Which of the following diagrams shows a particle level view of a surface section and interior section? Okay, so on the surface, there would definitely be some chromium, right? But they only need the chromium on the surface. And on the surface, there should also be some oxygen, because they mentioned chromium atoms interact or react with oxygen, and they form a layer of chromium oxide. That alone will probably just give you the answer. And so let's see what we get here. Okay, so here we see no chromium here anywhere at all. So it can't be this, and it can't be this. Right? So there shouldn't be chromium in. Wait, can I reverse this? Here, let me see. Reverse this. Okay, whatever. But there shouldn't be chromium here because this is the interior. But this example is good because here we see the chromium. We see the chromium, and then we see the oxygen. I made the layer, right? And this should be more interstitial, right? But not as interstitial as probably we'd like. But still, this could be valid. Yeah, chromium should definitely not be here and here on the inside and the interior. It could be, I guess it could be here. But let's see the other examples. Maybe there's a better one. Okay. Okay, look at these last two. This is not it. These are all chromiums on the inside. This is not what's going on, right? We have carbon on the inside, so this one is wrong as well. So C is wrong. And again, the oxygen are forming on the outside here, and this is inside. I forgot. This is the interior. So there's no oxygen on the interior. So this is wrong too. So there's only one right answer, and it makes sense. It's kind of super obvious. Look, the chromium is on the outside because it wants to make a layer where it hits with the oxygen and makes this protective layer. But inside, what should be interstitial should be the carbons for the most part. That's what we should be focused on, right? And this is inside. This is on the interior. So the answer would be B. Okay. This is one of the easier chapters, I feel like. Or sections, I should say. Which type of chemical bond is present in such as halogens and chlorine? And well, they're pi bonds, right? And so pi bonds would be like a double covalent bond because they're sharing. So like halogens, right? So let's it's an easy example of a halogen. Let's look at a periodic table. I'm thinking chlorine would probably be an easier one. Maybe bromine. Okay, so fluorine would even be easier. So let's say fluorine, right? And oxygen has 8, so fluorine. So oxygen has 8, so fluorine has 9, and then 2 of them are on the inside. So okay, so fluorine and its Lewis structure would be like this: 1, 2, 3, 4, 5, 6, 7, and then on this one would be 1, and then right? And then this would be, a covalent bond that's sharing the electrons. Probably a double covalent bond too. Okay, and then of the, because it's not just sharing these two, it's sharing another two as well. All the halogens have the same molecular formula. Which molecule will have the longest bond length? Choose your terms of atomic structure. So the smaller ones will have the longest bond length, because with the size, right, as the size increases, the bond length would decrease, right? So I would say fluorine. Of all of them, fluorine would have the longest bond length. So in atomic structure, if you look, fluorine has the first string of 1, 2, and then the next string it has 1, 2, 3, 4, 5, 6, 7. So there's less, what do they call them? Van der Waals interactions. Van der Waals interactions, which are example of intermolecular forces. And so thus, this would have the longest bond length. Okay. Cl2 reacts with the element Sr to form an ionic compound. That makes sense. Based on periodic properties, identified a molecule X2 that is likely to react with Sr in a very similar way. Oh, this is very easy. Any halogen, pretty much, at least I believe Sr to be a metal, right? And then this Cl was obviously the nonmetal in the ionic, right? In the ionic bond, right? The ionic compound. So yeah, it could be I2, it could be F2, and it could be Br2. And justify my choice, all of these are halogens. And most of the time, whatever Cl can do, these can do, because they all have 7 valence electrons. Okay. Graph of potential versus intermolecular distance for 2 chlorine atoms is given below. On the graph, carefully sketch a curve that corresponds for 2 boron. So on the graph below, carefully sketch a curve. So if you look at your periodic table, bromine has more rings, right? So its distance would be longer. So it would start here, and it would be something like that, only because its internuclear distance has to be greater due to sorry for my handwriting, due to increased intermolecular forces because of bromine's increased mass. Moving on. Okay, what is it? Hopefully one more question. Oh, I remember going over this question. Okay, this is a pretty easy question. So white gold, and this is true, is a common alloy of gold and palladium. And this is why there's some jewelry that looks like it's stainless steel, but it's actually white gold. And so it's often used in jewelry. This is very true. And the atomic radii of the metals are given in the... Okay, so the atomic radii virtually the same. Just give or take very little. A particular ring is made that is 75% mole gold and 25% palladium. In the box below, show a particle level diagram of the solid alloy consists of 12 atoms of representative proportion of. So they will just only want 12 atoms. So okay, we already know it's a 25 to 75, right? And so it'll be AU. There'll be 9 of them, and then palladium, which is PD, there'll be 3 of them. Okay, that's easy. Your diagram should clearly indicate whether the alloy is interstitial or substitial. That's all obvious. It's not interstitial, it's substitial. Use your empty circles for gold and shaded circles for palladium. Oh, super easy. So I'm literally drawing... okay, so I'll draw all 12 circles first, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then in the image, I remember they were just like spaced apart. So I would shade in this one. They said shade for which color? Shaded for palladium. So we're just shading 3 of them. So 1, should get a thicker pen to color crayon. Maybe that's better. Maybe that'll work better. So I'll put one here. No, that's not any better. What is this? Smooth lines. You know what? Maybe I'll just stick to this, right? But then I'll maybe. Aha! There we go. All right, now we are drawing and coloring in. Okay, and then maybe put one here. There you go. You got your 9 gold atoms, and you got your 3 palladium. And that's it for chapter or unit or section 2.4.